Hi, and welcome back to Book Club in this amazing book, Aircraft Engine Design. And remember, key Book Club, you, the reader, go through it, especially these wonderful examples that are in there that's kind of flowing from the aircraft all the way to design. It's basically designing a new F-16 throughout this book. Is what makes this book just a joy. And again, my role here as your guide in this reading expedition is just to provide the wave tops, keep you interested, the kind of key concepts, and then you really go teach yourself. That's really what I'm trying to empower you here to do at the Book Club. Okay, and we are now deep into the engine. So this is chapter 4. And remember I was saying all of our symbols are now about to change fully again, okay, which is hard. So kind of each one of these chapters, if you see an alpha, you got to just know the context, what the hell that alpha is. Okay, so starting off is first here, and I'll have to shift my head over here. These are the aircraft station numbers, the aircraft engine station numbers. Now this is fairly consistent throughout the industry. Excuse me. And so 1 is the fan inlet, and then 2 is sort of the compressor inlet. And yes, it is different. We'll talk about some of those differences. And then it really basically, like, because it's a 3, this is showing you 3 fans. 2.3 is the exit of the third fan. So if you see 2.1 would be the exit of the second fan, 2.2. So 2.3 is then the inlet exit. Now, aircraft, a lot of times will take some of this air is compressed a little bit, right? The fan is pushing. And so actually back to, this is called a bypass. Okay, so what's happening, you have the core of the engine inside, and what you're driving with the engine is a fan. Now, I know turboprops are usually what we think of an engine driving a propeller. No, a jet engine is basically the same thing. It's an engine turning a fan. Just the fan is just now usually at a higher speed, and we have to case it in for protection. It's also a lot more fans, if you will. It's not just like a 4-bladed propeller, things like that. So yeah, it's encased for safety and also for usually sound as well. Okay, and so the fan, this is now your bypass ratio. Now, this is a pretty small bypass ratio, so this is looking like a military engine. If this was a commercial engine, that fan would be really, really big compared to the core of the engine. And so station 13 is actually, that's not a 1.3, that's station 13. That's actually the bypass air of the fan. That's the fan going around the engine. Okay. And so then we start compression, okay? Right here. So this is then your compressor blades, and so then each row is then also considered compression. So this would be 2.5, 2.6, 2.7, 2.8, right? So you have all these compression blades, and then 3. So this is now where we split it. This is now the sort of the exit of the compressor. Now many engines, we'll get into this, is actually 2 spools. So you will actually have a high pressure turbine driving a high pressure compressor, so it can spin at 1 RPM. We'll get into why. And then you'll have a low pressure turbine which is driving a low pressure compressor as well as the fan. And usually those are linked, except for Pratt & Whitney actually did a geared turbofan where that low pressure spool was then it was geared to the fan, which you see up front here, so that the fan can operate at the speed it wants to operate at. So anyways, lots of details. We'll get through it throughout this book. Just trying to hit you the highlights of the station numbers. Okay, 3 is in the combustor inlet. So combustion is happening here. And then 4 is the combustor outlet. And now it's the turbines. Okay, so 4.1 would be at the first turbine blade, 4.2, blah, 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 all the way through all of your turbines. Again, the numbering doesn't, if you have a high pressure, low pressure split, you just kind of keep counting. 5 is the turbine exit. Then 6 is sort of the fanning out here, where you may, it's an exit versus the duct, because you're now bringing the core down. And so you may talk about trying to match the speed here between what's coming out. There are also bypasses that come through here. This diagram is not going to show you some of the bypasses that you might kind of sort of take off of the turbine. This diagram is actually showing you one bypass that's sort of coming out after this. And by the way, when you're on an aircraft and the air you're breathing is actually the air that's been compressed up front and you're actually taking a bleed off of that. So it's called that jet engine bleed. It's used throughout the aircraft for many things, but including for humans to breathe. Yeah, yes, they put a filter there, but it hasn't touched any of the fuel system yet. Okay, and then 6A here would be the start of your afterburners. Okay, and then 7 would sort of be the end of afterburning. 8 is then a nozzle. A lot of times these will have nozzles associated with them. Sometimes it's a converging nozzle. If it's simple, sometimes it's a converging diverging nozzle, which is kind of what this one is drawing. And then 9 is the exit of the engine itself. Okay, so I know this might have felt like we just kind of jumped in the deep end, but we're going to need all these station numbers to describe aircraft engine. And so hopefully I did a little bit decent example of sort of showing you why we're having all of this stuff. And again, just to sort of back out to the thermodynamics point of view, it's really easy. Suck, squeeze, bang, blow. And you're drawing in air, you're squeezing it to compress it, you're mixing it with fuel, and then you're exiting it. Okay, and you need to do that as thermodynamics. That's where you get work from. That's how you are able to extract. You have to, when you burn things, you make them hot. Right? In order to extract energy from the heat, you have to be at higher pressure so that you can convert that into flow and expand it over turbines. I mean, same thing's happening in your car. Suck, squeeze, bang, blow. You're squeezing the engine, you're adding fuel, and then you're pushing the piston. So that's where you get your work out in the car. So it's all the same stuff here, just continuous in a Brayton cycle, and so constant pressure heat addition. So we're talking about. All right. So the thrust. So here's where we're starting now after all of this. So I'm going to make this thing small. So still talking about this, but it's just the smaller version. All right. And the first one, come over here, is F, which we usually mean for thrust. I know I used T in the last slide. Again, you got to pay attention to nomenclature. Watch out for it. It is basically M.9 V9. Okay, this is the stuff coming out of the back of the engine, minus M.0 V0. Okay, now why didn't I use V1? Because again, it could be different. It's actually, you have to extend from 1 out to 0, which is the free stream. I'm trying to mean the free stream here. And so this is the mass in the free stream that's going to get sucked into the engine. Sometimes it can be wider, sometimes it can be smaller. All right, so that's the difference in sort of the momentum force. And then you have your pressure force plus A9, and then any difference that might be left between the exit pressure and the atmospheric pressure. Sometimes this helps, sometimes it doesn't. Right? This is a lot where your nozzle, the right nozzle will actually get P9 equal P0, and that's actually your most thrust. Now it makes this term go away. It actually makes this term increased. So anyways, you end up doing this pressure matching. It's the same thing in rocket engine. Well, your best performance is when your pressure is matched, not when you're sort of under expanded or over expanded. It's when your pressure is matched. Okay. So other couple differences. These are not the same because M9 includes M.0 plus your mass of fuel. Now, I know it's not a lot. Usually from an error ratio, this is maybe about 15 to 1. Okay, so it's 1 part fuel to 15 parts air. But it is there. Okay, so a lot of times you can ignore it for sort of simple assumptions. A lot of times that's not a horrible assumption. And a lot of times, even from a thermodynamic point of view, you just consider all of this air, even though it's not. Right? Even though this is now air and CO2 and water vapor. And and then nothing is ever perfect, so there's going to be some NOx in there. There's going to be some carbon monoxide in there, and so a lot of this has flavors of: are you making an assumption, or are you trying to be detailed and accurate? So it depends where you are in the design cycle. Sometimes you need to go do both. Other times, it's a 1%, 3% correction. You're not going to worry about. Okay, and so the main variable here is pi. Okay, this is basically your compression ratio. This is P2, right, over P1. Okay, we're going to write that P2 over P1 from the engine point of view. Okay, so again, 1 is sort of the inlet And it might be different than 0. That would be sort of difference between installed thrust versus uninstalled thrust. But by definition, this is going to be the compressor ratio. So you see pi, that'll be fairly consistent throughout the book, except for when you're actually using pi as pi. But pi is your compression ratio of the engine. And so everything, all the performance usually is driven by that compression ratio. And that's what we'll see. All right, and so T2 over T1 is actually, you go do the whole isotropic relations, and you get, this is pi gamma minus 1 over gamma. So this is back to what you can find is the compression ratio is what drives your performance, it drives your fuel efficiency, but it also drives your temperature. So you're going to have a limit, okay, where you can't melt. Compressing the air more will actually melt the engine. All right, bypass. Unfortunately, this is one of those annoying alpha. Is the bypass, and so this is m dot bypass versus the m dot that's going through the rest of the engine, through the core. I'll just use MC for core. Okay, that's bypass, unfortunately, and then beta is now the bleed. M dot bleed compared to m dot core. Again, in that picture, remember I was saying that you take some air away from the engine and use it as bleed. It goes to aircraft systems, it goes to passengers if this is a passenger aircraft. The other thing it does is that bleed air is actually now also used. I'll show you some pictures of it when we get to the components chapter. That air is actually used to cool the internals of a couple of the turbines to keep them from melting. Okay, it goes back to this. You actually are. The temperature T2 is already going to get hot, and then you're going to add fuel, which is going to make it hotter. So performance is going to be related to compression ratio. It's also going to be related to that temperature. So the higher you can bring that temperature, the better your performance is. The higher the temperature eats into the lifetime of the engine, and so there's actually quite a bit of cooling technology that goes into those turbine blades, from internal cooling with its bleed air, as well as what are they made out of. There's some pretty advanced technologies there. GE has done a lot with metal matrix composites. There's thermal barrier coatings on those blades a lot of times. Some of them are actually like single crystal growth, so that when they're spinning at these rates, it's very controlled. Anyways, we'll get into all of this. Honestly, the turbine engine is one of the most glorious feats of human ingenuity and engineering ever. It really is. You're going to see some of that why. So beta is now bleed. Okay, I remember last chapter, alpha was thrust laps, and beta was weight of the aircraft. Now we're in the engines. This is bypass ratio and bleed ratio. All right. And then F usually is m dot fuel over m dot air, little f. Okay, so pay attention to that. And then thermodynamically, I'm going to just write down what are some of the, I'll try to do it here. What are some of the efficiencies, okay? So eta will be a list of efficiencies, and I'll kind of list them here. So the fan efficiency is pretty darn good, okay? That's running roughly about 92% fan efficiency. That's the efficiency of the fan. It's not bad at all. The compressor efficiency 91. The diffuser is 97 to 99, so we do pretty good there. That's the diffuser into the combustor. The turbine is 91% these days. The afterburner is about 90% efficient. What else? The nozzle is 98. Yeah, nozzles are pretty good. 98 to 99%. What else did I write down? Okay, so that gives you a rough idea of efficiencies. So it all stacks up. So you can't, for sure don't just assume isentropic everywhere. When you're doing your engine balance, you would do all of this stuff. Oh, by the way, this book is also going to talk about the software they have sort of available to kind of run a lot of these things. So take a look at the software. It's been a while since I used it, but it's anyway, it'll help like with a lot of stuff if you're actually really wanting to play and kind of poke around with your own design. You're quickly going to want to use a software like that. You'll just see that quickly these calculations get gnarly. So there's a lot of free software out there. Don't reinvent the wheel. On some of that. Okay, we talked about temperature, so I'll do that here. So this is temperature T4. Okay, back to the diagram. T4 is combustor exit going into the turbine. These days, that's about 4,000 degrees F. Okay, that's sort of the estimate of where we're heading with these kind of metal matrix composites and all these. I mean, sorry, this would be like advanced engines that are kind of starting to come off the shelf this generation, kind of the next five years or so, right? To give you an idea where this has been, okay, it was 3600 F and then 3200 F, and I'll do this in orange. This is sort of 2005 to 25 time frame, and then this was sort of 95 to 05 time frame. And so, yeah, to anybody out there who thinks like the jet engine has been solved or there's nothing happening, no, this industry continues to evolve. Now, there's actually quite a bit that goes into it. If you think of all the aircraft, all the power generation system, all the turbine engine industry, it's actually a massive, massive industry. And I remember being a professor and I think it was at a conference in 2006, something like that, and the head of Rolls-Royce engines R&D was saying a 0.1% increase in engine efficiency was worth something like $1 billion worth of research. That just gives you the scale of the engines, and that's where a lot of this is coming from. Okay, so I already mentioned GE has done a lot of work with sort of metal matrix composites, and this is roughly why it's going to start paying off for them. Okay, so that's pretty awesome. All right, and then T7. Okay, T7. Look at the diagram. That's sort of afterburner exit temperature. Afterburners usually can handle a little bit more. Some of it is actually you have some of the air from the bleed that's sort of providing a little bit of a barrier. If you take a look at afterburners, there's also kind of these ducts that try to keep the flamey part on the inside, and then you run a little bit of cool air. It does mix a little bit. You're not going to get away with that. But basically, where we're headed is 4400 F is where. Oh gosh, that's off the screen. Okay, a little higher. 44. You guys see that? Okay. 4400 F is where we're headed. Historically, now 4000 has been about right, and then 3600, kind of late 90s. And so you can actually if you keep going back, the book does talk about it, like why some of these engines, kind of first engines, some of the kind of Century Series fighter jet aircraft and things like that. Yeah, they're not that efficient. I mean, we've really engine efficiency's really come a long ways. And honestly, it's enabled some pretty amazing aircraft. Okay, from a military point of view, supersonic is now like considered supersonic cruise, where that means you are cruising without your afterburner on. That's now basically a requirement for almost any fighter these days, and that just shows you, just honestly, how much has come along. Okay, and just a reminder, and I covered this in some other classes, and I know for sure I've covered this. And so that Venus high-speed flight series, but you can think of your overall efficiency as really three terms. Right? You have sort of your thermodynamic efficiency, which is going to be related to your compression ratio. You have a jet efficiency, which is how well is this jet sort of mixing with the free stream. How well is it adding to it? And then your isentropic efficiency. You can think of it as sort of the smacking of all three. And this isentropic efficiency, if you will, is kind of the stack up of all this different stuff. All right. And just as a reminder, your thermodynamic efficiency is basically 1 minus 1 over pi. And that rates to the gamma over gamma minus 1. So compression ratio is driving efficiency. And then your jet, you go work it. I know sometimes this looks a little funny. Go look at the derivation. You'll see why this is not that funny at all. It's basically the kinetic energy. This is relating V0 to your V jet. And so your most efficient efficiency here is basically when the speed is the same as the inlet speed. So that's one of the reasons why bypass engines work really well. It's actually more efficient. This term gets more efficient if you take a really big fan and a whole lot of air and basically barely add any speed to it. You basically maximize that thing. Okay. All right. And so then where you end up drawing is okay, S before used to mean wingspan. This is now specific fuel consumption. Specific fuel consumption. Now I'm more of a rocket guy, and so this is actually inverted for me. This is 1 over ISP. So specific fuel consumption, you want to go down. Again, the rocket world specific impulse, you want it to go up. This versus a lot of times you'll draw this as specific thrust. Okay, the book shows some plots like this. Okay, and I'll draw here where this is no bypass and this is bypass, so my 0.7. And so you can see a little bit better. Boom. You can see here that you might almost get a doubling of your efficiency from going to a straight turbojet. That's what alpha 0 is, versus a high bypass ratio. All right, and then this would be pi of 24, and I believe this is pi of 8. And so that's kind of giving your idea of those are your main performance drivers. Honestly, like that's it in a nutshell. Everything else is sort of I won't say secondary. There are certainly these. Don't get me wrong. These things matter. These stack up here of efficiencies matter when you're talking about this. But this is basically it. Now remember, I showed on here alpha. This is basically a surrogate for, hey, this eta jet is driven by how much you have here. So a larger alpha is going to mean that V jet is closer to V0, and that's basically it. Like those are your two primary drivers for fuel efficiency. Okay, and then like I mentioned before, I'll just go to draw it again here for completeness. Those don't come for free. You might just say, well, then let's have a big massive alpha and let's have high compression. No, it's not for free. Okay, so first one, this is basically your theta, right? And this is total pressure at 3 versus, I can't read my own writing. I think it's a P standard. All right, this is effectively your theta break. Okay, and so you're going to ride. You end up riding your engine will ride this performance curve, and then in orange here I'll sort of draw these lines of constant theta. Okay, and so what's going to happen? By the way, 4,000 is usually a theta of 6. That's roughly where this 4,000 limit is going to sit. And so this would be, say, 5, 6, 7. And so you're going to run your compression ratio. You're going to run it at that sort of standard compression ratio, and then you're going to fall down this line to sort of keep your system from melting. Okay, so it's called theta break. All right, and then let's say your performance again, T3 is also T3, which is sort of your combustor inlet. That's going to be related to how much you can handle as well. Okay, so that's sort of the final one to keep in mind. This is then T3 versus compression ratio, and generically they just go up like this. Okay, so this would be theta equals 1.2, theta 0.9, and this is theta 3. Okay, and so it's increasing this way. So the higher your compression ratio, you're going to have issues with sort of your last combustor, or being too hot coming out of your last combustor, where things are going to melt before you have, it's going to start melting everything downstream. So you have a limit there, and then you have sort of that overall theta break system where you have to, your airplane can go up. you can ride one performance curve and then you're going to have to get off of this. Basically, most engineers would call this off design, and what we're going to see is the word off design might still be valid, but it's basically like every mission. So this is not some weird thing that happens. You're going to have to design this engine to sort of operate and sort of in these two modes. One where it's you're driving at this pressure, another where you're basically dialing back on your fuel. Okay, so if you're a pilot, that's why a lot of times you'll have turbine exit temperature is one of the sensors you're going to have in your screen, and some of the automated systems will just follow it, but it's one of those things you're going to pay attention to as a pilot, is that turbine exit temperature and how hot it is. Because if it gets too hot, that's the sign that something upstream is getting too hot. All right, so those are your main performance characteristics. And so as we sort of now have had the high-level aircraft design point of view, this is now what's driving the engine, and now we'll kind of start this sort of back and forth with the aircraft and profiles and engine performance that's sort of related to this, to sort of hone in on the aircraft and kind of speeds and altitudes and things like that. So it's pretty fun. All right, so get into the book, dig in, read, especially those examples. They're phenomenal, and we will see you next time.